Okay, it's 9:40, so let's get started. So quiz 5 is out, and it's due Saturday, just like all the other quizzes were, so get started on it. Part 2, homework 2 is due on Sunday. So how many of you did something with part 1 of homework 2? There's a few very low rate hands, right? But if you didn't do part 1 or really any of the parts so far, I highly recommend doing them. You give excellent feedback, and it's really helpful to know what things that you're missing, what things you don't understand quite well. It's very useful. Okay, so any questions before we get started? Yeah.
From lecture on Tuesday,
Yeah.
so is it like that black and white where it's like, if a grammar is not regular, is it automatically context-free?
No. Here. Well, if you have a context-free grammar, it is context-free by definition.
So it's not regular?
Not necessarily. You may have a grammar like this. It only has the string 0, 1 in it, and it's definitely not a regular grammar. But I think just a single string is regular. But if a language is not regular but context-free, then there definitely is a context-free grammar for it, but there is no regular grammar for it. Yeah, so just because, you can show that every single regular language is context-free because every regular grammar is a context-free grammar by definition. So you know that every regular language is context-free, but not the other language. Okay, does that answer your question?
Yeah, that makes sense.
Any other questions? Yeah.
While converting from DFA to regular expression, does the order of ripping states affect the regular expression?
It affects the presentation of the regular expression, but if you apply the method correctly, the language of the regular expression is the same.
The final expression will be the same.
The language will be the same, but the regular expression itself will look different. Yeah. Almost certainly, yeah. But that's just a problem with creating that type of question because it's like, I can't have a single answer to look at it. I have make n factorial different ways to look at it. So, any other questions? Okay, so what was the major thing that we talked about in lecture last week and Tuesday? Yeah, this pumping lemma business, right? So what in the world is this pumping lemma? Pumping lemma. What does that have to do with anything? Right. We were able to show that some languages are not regular using this. But what does the pumping lemma actually say directly? What does it say something about?
So like if you meet 3 conditions.
Yeah,
like
way before that. Way before that. The very first part of it.
A pumping constant.
Even before that. What does it say something about? Yeah. I'm not going to worry about the DFA here, but what thing does it actually say? Something very close to that, though. Something related to DFA. The DFA has what kind of language? Regular. Oh, I think pumping lemma says something about regular languages, right? It says if you have a regular language, then I have some properties. But wait, then how can I apply this to show something that's not regular? Oh, if I assume that it's regular for a language that I want to prove non-regular, then if it fails to meet the conditions, then there's no way it could have been regular in the first place. Okay, so if I have a regular language L, then what can I say based off of this statement? If L is regular, then what can I say?
It has a DFA.
Well, it has a DFA, but the suggestion from earlier, which is?
Pumping.
Yeah, there's this pumping constant, right? So there exists a pumping constant P for L. And what does this P represent? Well, it's pumping length, but what is it trying to represent in our head? We're thinking about what in the background? Something to do with regular languages? Every regular language has that? Has a 3-letter acronym, please? D, F, A. Thanks. What do you think this P represents? I know it's early, but come on. What does this P represent? I think a diagram might help. So if I have a DFA right here, and what did we want to happen with this DFA? A loop of state, right? And how did I guarantee that a state will be repeated on some input? How can I guarantee that a state will repeat? Well, how can I guarantee a loop will happen? It may happen with some strings, but how can I guarantee that it'll happen?
Can you put string longer than the number of states?
Right, I have a string that has length at least as large as the number of states. So let's say I have this string like that, and let's say that this is the repeating state. And so this is a little bit misleading. It may be the case that all 3 of these are the same. It may be the case that only 2 of them are the same, or maybe they're all different. I'm just depicting them as all different. Well, let's say that this is the state that repeats in the middle. Well, I have to assume something else about the string. It's accepted by the DFA. Okay? So I'm talking about a string that is long enough so it repeats the state and is accepted. So let's see. If I look at that particular string, well, it comes to this repeating state on some input characters. So maybe 0, maybe a whole bunch. Well, I'm going to call that string X. I said that this state repeats, so I have to come back out, and then come out and then come back on some string Y, I'm going to call it. And I said it is accepted, so therefore I should go to some accept state. So let's say it's this one. And I say I call that Z. Okay? Well, is the string X, Y, Z in the language of this DFA? Yeah, because I just follow the path. What about X, Z? Yeah, that's in there. X, Y, Y, Z. Any number of Y's in the middle, would that work? Okay, so from this one string, this X, Y, Z string, I know infinitely other strings that are in the language, which I think is pretty interesting. But let's get back to what the pumping lemma says and how it relates to this. So P is going to represent the number of states in this DFA, in some DFA for L. So I'm not going to be talking about a DFA here. I know that there is a DFA for it, and that's what it represents. Well, let's see. How did I get to this point? Well, I have to have this repeating state, and so how did I guarantee a repeating state? I have to have a string longer, or at least as large as the number of states. What part of this represents the number of states? I think the P thing, right? Okay, so for every string that's in the language, because it ends up in the accept state, and at least as large as the number of states, which is P, then I can say something about that string, that there are other strings in the language. So let's see. For every W in L with length of W at least P. Right? I can only talk about strings long enough and in the language, right? I can't say anything about other strings here. Well, let's see. If I have such a string, I call it W here. Well, W right now is X, Y, Z, right? I broke it up in X, Y, Z. Then if I have this property, there is some way of breaking it up into X, Y, Z. So there is a way to write W as X, Y, Z, so that, and then now we gotta say something about X, Y, Z and what they look like. So We have our three conditions from before. Well, I think you'll agree with me that x, any number of y's that I want, at least 0, z is in the language. I think we came to that conclusion before. So how do I write that as x, any number of y's that I want, z? X, y to the I, z, for any value of I. Is it in the language or not? Right, it's in the language because we all agreed that it went to an except state. So x, y to the I, z is in L for all I at least 0. Well, now we got to figure out what the other two conditions are. So what are the other two conditions?
Y variance, length of y to be greater.
Right, I can't have y to be empty. So two ways of saying that are the length of y is at least 1, and another way is that y is not empty. Why would I want top y? How come I want this condition?
Because if it's epsilon, then that would make everything.
Okay, yeah, exactly. So if y happened to be the empty string, then I don't think this statement tells me very much. Put as many copies of the empty string as you want. Am I going to get another string? If I keep putting empty strings in, I don't think so. So this won't tell me very much. So I have to say y is not empty. And another way of thinking about that is, this is a state that repeats. So there must be a transition, at least one, from this state back to this state, because that state repeats in the computation. So I have to have at least one transition there. So that's why the length is at least 1. But what about the first condition? Right, so the length of x, y together is at most p. And so why do we even have this condition? It actually turns out that this is not strictly necessary in general, but it makes our lives a lot easier. So why would we want this condition? Well, let's see. We know that this works for all strings of length at least p. What if I consider the strings of length exactly equal to p? Would it still work? Yeah, I think so, because I said at least as large as p. So p would have to work here. So let's think about a string of length exactly equal to p. Well, what does that mean? I still have to have this repetition, right? Because I said it works for strings of length at least p, so the p length string will still have to work. Well, there must be a repetition, so therefore some repetition must have occurred within the first p characters. So for any string that I feed, within the first p characters, there's some repetition that happens. There may be other repetitions that happen, but I know at least one occurred within the first p characters. And y is the repeating part. Well, I note that x came before y, so therefore x couldn't have been at least the p character. So x, y together is not longer than p, because it's the beginning of the string. Okay? Are we good with this? So now let's actually use it to prove things not regular. So the example we did in class was 0 to the n, 1 to the n. So now I'm just going to extend it a little bit. So now we have 0 to the n, 1 to the n, 2 to the n. And I claim that this is not regular. Oh, wait. Pumping Lemma says, if L is regular, then a whole bunch of stuff is true. I want to show that this is not regular. I don't know if it is regular yet. I can't use this. Can I? Oh, okay. Maybe if we assume to the contrary that this thing is regular, then we can reason about some of the things here and hopefully get a contradiction out there. So let's assume L1 is were regular. Well, let's see. What does that statement alone tell me with regards to this?
That should satisfy that, so it should be a constant P.
There's a constant P for L1. Good. There exists a constant P for L1. All right. Let's see. I think I want to get a contradiction out of this. Hopefully. Well, let's see what this says, and maybe we can reason about how we would go about doing this. It says that once we have this constant P, then every single string in the language that has length at least P essentially means can be pumped. Every single one works. Oh wait, if I want a contradiction, if I show you one string that I can guarantee can't be pumped, I think this for every part is false, right? And if I show you one string that doesn't work, then I think we're good. So I think my goal now is, let's pick a string. And what two properties do I want of this string? It has length at least P and is in a language, good. So choose a certain W. And so I want this string to have length at least P and in the language. And so I guarantee you on the midterm, if we happen to have this question, someone will write this string. It's in the language, right? Equal numbers, zeros, ones, and twos. But what's the problem? It may have length at least P. I don't know. I don't know what P is, right? So how can I guarantee for this string to have length at least P and stay in the language? Is there something I can modify here? Okay, maybe I could have P0s, P1s, and then P2s. Okay, maybe let's try that. I think it's still in the language because zeros, ones, and twos are all the same, and it has length 3P, which is definitely at least P. So we're good there. Maybe the string won't work eventually. Maybe it could be pumped, but at least we can actually try this one. All right, so it says, here's the string that I want to prove a contradiction for. And so let's see. It says there is a way to write W as X, Y, Z so that you can pump Y in. Well, it says there is a way. But if I want a contradiction, I think I need to show every single way it doesn't work, right? If I happen to leave one possibility out, that may be the way that works. Because the lemma says that there is some way that works. It doesn't say every way works. It says there is some way. So I think I need to look at every way to decompose the string into X, Y, and Z. So now I gotta think about what can X look like, what can Y look like, what can Z look like. Okay? So let's think about that. Well, let's see. X is the beginning of the string, so it has to contain some number of zeros. But could it contain ones or twos? No. And how do you know that?
It has to be less than X, Y.
Oh, yeah. The length of X, Y together has length at most P. Oh, what does that tell me about what the X's are? I think they're all zeros. X is all zeros. Okay. Oh, does that tell me something about Y then?
Yeah.
Yeah, it also tells me why, because X and Y together don't have more than P characters. So the first P characters are all zeros, so there's no way Y could ever hit a 1. Okay, so I know X and Y are both all zeros. Well, let's see. But then again, I gotta handle every single way to decompose it according to these rules. Well, I know X is all zeros, but let's just say it has some number of zeros. I need to handle every possible way. So let's say it has A zeros for A at least 0. Because X could be empty. I never said X can't be empty. But for y, it may have the same number of zeros as the x part, I don't know. I need to handle every single way, remember. Let's just say it has b zeros, for example. Do I know anything about what b is? Or a lower bound on it, at least? Can b be 0? No, and y can't it be 0? Oh, that's the second condition. The length of y has to be at least 1. It can't be empty. Okay, so I know b is at least 1. So we won't be using the fact that a is at least 0 here, but we will use the fact that b is at least 1. Okay, but now from this, I got to figure out what z looks like. Well, let's see. I think z is the rest of the string because there's no other parts of the string. So let's see. I started off with p zeros. I took away a. I took away b more zeros. So I think I have left p minus a minus b zeros. And since I never hit the 1s or the 2s, I have all of those guys left for the z part. I'm just breaking the string up. Okay? So now let's think about what part of the lemma is going to actually give me a contradiction or help me give it. So what part is going to help me get a contradiction? Something we haven't used yet. Yeah, number 3, right? Well, let's see what it says. It says that if I pump in I copies of y into this string, it will always stay in the language for every value of I, every odd ones. So for a contradiction, I think I need to find one value of I that gets me out of the language. Okay, so now I gotta choose some value of I. For this string I currently have, what value of I have I chosen so far? 1, right? Yeah, because I only have 1 copy of y, so I think I need to choose something other than 1. And look, it'll actually turn out every value other than 1 works for this, but you guys can give me any value that you want. 2, that's perfectly good. Why not 473? I don't know. Let's look at x, y squared, z. And I want to show that this is not in the language to get the contradiction that I want. So what is the x part? Well, that's just a zeros. 2 copies of y. Well, I think that's 0 to the b twice. So 0 to the b, 0 to the b. I just put in b more zeros. And the z part afterward. So I have p minus a minus b zeros, p1s, p2s. Well, I have a bunch of zeros in a row. I think I can simplify. Well, let's see. I see a zeros in a row, and then I subtract a zeros, so I think that the a's are gonna cancel out. And I think I have a b set of zeros and a subtract b out, so those cancel. So how many zeros do you think I have left? P plus b, yeah. Because I pretty much just added b zeros at the beginning anyway. So p plus b, 1 to the p, 2 to the b. So that's the string I currently have. What's my goal with this string? What do I want to show? It's not in the language, right? So what's the only way it could have been in the language? Well, let's go one step at a time. Well, the only way it could have been is if the number of zeros, 1s, and 2s is the same. Well, I think that means that p plus b is equal to p. So that's what this tells me. Oh, but then we can subtract p from both sides, and that tells me b is 0. Is that a contradiction? Yeah. So the contradiction comes from the fact that this and b at least 1 can't work together. Okay, so what can I conclude directly from this? About the string itself, x, y squared, z. It's not in the language. Good. So this string cannot possibly be, and I called it L1. So then what can I conclude about L1? It's not regular. So L1 is not regular. Okay. Everyone good with that so far? So the recipe pretty much is exactly the same for all of these. All right, so second one. The only difference here is that I have 3 n0s and 2 n1s and the same number of 2s. So I just basically made a small change to this language. And I claim that this is also not regular. And you can actually kind of see why, because number of zeros depends on the number of ones, which depends on the number of 2s. So how can I start this? Yeah.
Can I ask a general question?
Yeah.
So let's say we're going to solve one of these problems and we get to the point where we choose a string like we did before, and then we make our own x, y, z. If it ends up that we can't figure out that it's not regular, we can't make a contradiction, do you recommend like going back and, so at that point we just go back and change the string or the x,
Yeah.
y, z? I guess you can't change the x, y, z.
Well, assuming that you broke it up into all possible cases,
You can.
if you correctly, then the
Yeah.
string is just happens to be a bad string.
Oh no, I'm sorry. I meant, do you change the power of the y? If that, like, if you pick 2 and 2
Well-
doesn't prove the contradiction.
Well, I'm being entirely general right here. Oh, you mean right here?
Yeah. So like.
Yeah. I would just recommend changing the power because I only need one value of I that works.
Yeah.
So if you find one value of I, that's enough.
So after we change that a couple times, if it doesn't work, then go and change the string.
Yeah, that's what I recommend. Yeah. But a good strategy with this is if you see an n in the exponents up there, put the p there. That usually will work. About 98% of the time that'll work. And actually for all 4 examples we'll do today, that's what will actually work. Well, except for the last one a little bit, but okay, well for this one, how do I start a proof like this? Assume that it's, we're regular, so I'm not going to write it again. Assume that there's a constant p for L1 bar. So what string do you think would be a good one to pick for this one? Right, I just put the p where the n is in the exponent. Yeah, it's going to work exactly the same way. So w is 3 p0s, 2 p1s, p2s. So is it? Sorry. What's going to change about my decompositions then? Do you think the x part's going to change? I don't think so because I have more zeros now, and there's no way that I could have more than p zeros, so there's no possible way that x is going to hit anything other than zeros. So I think that x part's going to be the same, and for the same reason I think y is going to be the same. Okay? I think the z part's going to change a little bit. Well, let's see. I should say b is at least one here. I started with 3 p0s, took away a, took away b. So I think when the dust all settles, I have 3p minus a minus b zeros, 2 p1s, and p2s. All right, it's almost exactly the same as here, but work with the string I currently have. Okay, so what's my next goal? Pick a value of I, right? I need to pick a value of I. So, any preference for a value of I? And any value other than 1 will work for this one too. 2. Feeling adventurous, want another value?
0.
0. Let's do 0. They're actually the only recitation so far to pick 0. But 0 is perfectly good. So what do I want? I want x, y, 0, z. What is any string chosen 0 times? The empty string, right. So that's just x, z. And so I think I just need to copy down my x part and my z part. So that's just 0 to the A, and then my Z. 0 to the 3P minus A minus B, 1 to the 2P, 2 to the 3. Okay? So how many zeros am I going to have left? The 3P minus B. Good. 3P minus B, 1 to the 2P, 2. What's the only way that this string could stay in the language? Well, it's slightly different from here. 3 times the number of 2's, I think, should be the number of zeros, because that's the only thing that changed. So I think this tells me that 3 times that number is equal to this number. So 3P minus B is equal to 3P. Oh, but then we can just do a little bit of algebra, and what is the conclusion from this? Would be a 0, but I think that can happen, right? So what's my conclusion? Well, first of all, that the string is not in the language, L1 prime. But what can I say about L1 prime? It can't be regular. Good. So L1 prime is not regular. Okay. Any questions about that? Okay. So let's do at least one of the more interesting ones. So the proofs for these are really cool, and it really illustrates the fact that DFAs are incredibly not powerful. So they can't even recognize perfect squares. So the language I want is just entirely zeros, so no 1s and 2's here, make our lives easy. And the length of the number of zeros is a perfect square. So empty strings in there, a single zeros in there, 4 zeros, 9 zeros, etc. And I'm claiming that this is not regular anymore. So how do I start a proof like this? Assume it's regular, right? So assume L2 were regular. And then what can I conclude from that? There exists a constant P. Constant P for L2. What's my next step? I gotta pick a string, right? Good. So choose W equals, and I guarantee you, if we have a question like this in the midterm, someone will put this. Is it length at least P? Right? That's a good condition. What's wrong with that string? Can I guarantee that P is a perfect square? Perfect square starts with a P, right? Oh, I can't guarantee it's a perfect square. Oh, maybe what I could do is I put P squared there. Is this string a good candidate? Yeah, P squared is at least P, and is in the language, so we're all set there. Good. And so now let's think about all decompositions again. Well, can I say anything about X and Y and what they look like? Yeah, they better all be zeros, right? The whole string is a bunch of zeros. So that's actually one of the reasons why working with a language with only one character in it is so much easier for this very reason. So X is some number of zeros, and Y is some number of zeros, and let's remind ourselves B is at least 1. And the Z part's going to change a little bit. I started with P squared zeros, took away A, took away B, so therefore I think I have P squared minus A minus B zeros. Okay. Same as before, just working with a different string here. Okay. So what's my next step? I gotta choose a value of I. Good. So I let you guys pick one value of I for the last two ones. Now it's my turn. So I believe every value of I other than 1 will work, but I'm going to pick one that's the easiest for analysis, that I know definitely works. And this can be I equals 2. I'm very not adventurous. I don't want to venture out too far with these. Well, let's see, what is this? That's x, y squared z. Well, let's see. Let's just copy everything down. So this is 0 to a. I'm going to shorthand y squared, that's 2b zeros. And z is 0 p squared minus a minus b. So what is the string I'm going to have at the end? P squared plus b. Yeah. P squared plus b. Okay. Now, what's the only way that this string could possibly be in the language? Well, it better be the case that p squared plus b is a perfect square, right? That's the only way it could stay in the language. Well, I can't immediately see the contradiction here. It may be a perfect square. I don't know, possibly. So let's figure out how we can go about showing that it can't be. It eventually won't be, but let's see what happens. Let's look at p squared plus b. Is p fixed? Is it a fixed integer? You sure about that?
Yes.
Yeah, I fixed it right here. What changes? B, right? Once I fix p, the value of b could vary, right? Between a certain number of values. Wait, what's the smallest value that b could possibly be? 1. 0? 1. I just said it has to be at least 1, and the reason was that the length of y is at least 1. So what's the smallest value that this could take on?
P squared plus 1.
P squared plus 1. It may be equal to that, but it can't be anything less than that. What does that tell me about p squared and this? Can they be equal? P squared plus 0 and p squared plus b. Can they be equal? No, because this is the smallest it possibly could be, but this is strictly less. P squared is strictly less than that. So can this be equal to this perfect square? Come on. No, right. There's a strict inequality there. So we know it can't be equal to that perfect square. But you say, well, b could be a larger value, and so reasonably, it could be equal to some other perfect square. Well, let's see. What's the largest value that this could possibly take? Instead of the smallest, let's look at the largest. Well, p, that's not going to change. But what is the largest value b itself can take? Well, let's go over here. I know it can't be larger than p. Could it be equal to p? Yes, because do I say anywhere that x had to be non-empty? No, it could be empty. So I think this could go all the way up to p squared plus p. So let's see. What I want to show is that if I can find that no perfect square is less than or equal to this and at least p squared, then we're good. So what's the next perfect square after p squared? Next one. P squared, then p plus 1 squared. Let's see what that is. Maybe it has some relation to this. Let's see. What does that FOIL out into? So let's put on our middle school algebra hat on, right? What does this FOIL out into?
P squared plus 2p
Plus 2p plus 1. Oh, let's see. I know that there's a p squared in both of these, and this guy has a 2p and a 1 in it. And that has a p in it, so I know that this is definitely less than p squared plus 2p plus 1. But is it a strict inequality, or do I have to put an equal on it? Could they be equal? No, and why is that?
Because the one after has 2p.
But p could be 0. The plus 1 gets us. So if p is not 0, then the 2p is definitely more. But if p were 0, then the plus 1 will get us. Okay, let's try to recap what we just saw. This is the length of a string that I just made. And these are the extremes for which it can take value, the largest and the smallest things that it can take value. I think, are these consecutive perfect squares? Yeah, I asked for the next one. So it's strictly between two consecutive perfect squares. So can it be a perfect square? No, because I asked for the next one, there can't be one in the middle. So what can I conclude about this string?
It's not.
It can't possibly be in the language. Okay. And so I think we can conclude from that that L2 is not right. Very cool. Okay, any questions about that? So now let's do I think, even cooler one. So hold on to your hats for this one. Because it's going to be a wild ride. All right, so let's do L3, which is almost exactly the same, but n is prime. Actually, not even close, because they're not even close to the common. All right, yeah, they're disjoint. But it's still a unitary language. And so how do I start this proof off again? How do I start it off? Assume it's regular, so assume L3 were regular, and then we know the drill by now. Exists P for L3, just to save writing. Okay, well, let's see. What's my next step? I gotta pick a string. So let's choose, so I left the space here for a reason. So choose W equal, and I guarantee you, if we ask this question, someone's gonna put 0 to P. P means prime, right? So therefore, this string is definitely in the language. What's wrong with that? P may not be prime. Well, I think I need to pick a prime at least as large as P then, right? I need to pick some prime so that it stays in the language. Do I guarantee a prime exists at least a certain value? How many of you have seen the infinite infinite number of primes proof? No one? It's beautiful. Look it up by Euclid, infinite number of primes. Well, if there are infinitely many primes, can they all live less than P? No, there must be one at least as large as P. Okay, so let's choose that one. So let's look at of any prime that we want at least a value of P. So let R be a prime at least P. And then I'm going to look at the string R. 0 to the R. But I'm going to make a very small adjustment to this, and then we'll see why I'm making this small adjustment later. So I'm going to make it at least P plus 2. And we'll see why in a second. Okay, well, instead of going the approach of looking at all decompositions of the strings and looking at what the string looks like, I think I only need to be concerned about the length of the string, right? But just like before, I was only caring about the length of the string, so let's try to go along that route and try to look at the length of the string. Well, let's think about what the decompositions would have looked like. Well, I think xy has length at most p, right? It has to. So can I say anything about the length of z? z in this string? Well, let's see. This has length at least p plus 2. So what is the smallest value of z could possibly be? 2. It can't be any less, right? Okay, so I know from this that the length of z is at least 2. Okay? What is the definition of prime? Divisible by 1 and the prime itself. I'm going to find a number in this language that's divisible by 2. So that's how I'm going to do this. Well, can I say anything then about the length of xz together? Well, I know it's at least 2, but can I say anything else? I don't think so, because it may be the case that x is empty. So I can only guarantee it's at least 2 here as well. So what's my next step? I gotta find the value of I that works, right? But it's not immediately obvious to me what value of I should pick. So let's just look at it in general, and then we can find out what value of I works. So let's look at, instead of a string now, I'm looking at the length of the string. So x, the length of x, y to the I, z. Equivalently, I could have said 0 to that length, but I'm more worried about the length of the string. So I want you to agree with me on several things. Is this length equal to the length of xz plus the length of y to the I? Does that seem reasonable? Yeah, because I'm just doing concatenations here, and the length of a concatenation is just the sum of the original 2 lengths. So no problem there. So I want you to agree with me on something else. Is this one up here equal to the length of xz plus I times the length of y? Does that seem reasonable? I think so, because if you have y to the I, then that's just I concatenations of y. Well, whatever the length of y is, I have I copies of it. So it's just I times the length of y. Okay? Are we good so far? I want to get a contradiction. So what I want to happen is, if I can show that I can have a product of 2 things, both of which are at least 2, then we can get a contradiction, because that product cannot possibly be a prime number. Well, I have one already, xz at least 2. So I want the length of xz to be multiplied by something, right? Well, I have an xz right here, so essentially I should be doing a factorization out. So if I factor xz out, what do I get? If I divide the length of xz by the length of xz, I get 1, right? So I get 1, so that's not enough to guarantee me anything. What is the length of y guaranteed to be? At least 1. Maybe I could put the length of y right here. If this number is at least 2, so we're good. But how can I get from here to here? What value of I should I pick? You sure about that? I'm factoring out an xz. So the length of xz should be the value of I. So let's choose I equal to the length of xz. Can I do that? Let's just make sure I'm not cheating. Can I do that? Yeah, all I'm doing is picking a value of I that is a finite integer. Well, concatenation of 2 strings, their length better be a finite integer. So I'm perfectly justified in saying this. What is the length of this? At least 2. What is the length of this? Also at least 2. So the length of whatever string I just found has length something at least 2 times something also at least 2? Can that be a prime number? No, because remember, primes can only be divisible by 1 and themselves. Well, it's divisible by something at least 2 and something else also at least 2. So it can't be prime. So what can I conclude from all this? The language cannot possibly be regular. So it is prime. Well, the string's not in the language, but L3 is not regular. This turns out to be a very difficult language to work with. When we talked about context-free in lecture yesterday, it turned out this language is not even context-free either. So it's a very difficult language to work with. But do you see how that actually went? I know it's a bit convoluted, but the idea of picking something based on the decomposition for the value of I is perfectly okay. I don't have to pick a concrete integer every single time. I can pick something based off the decomposition. That also works. Most of the time you'll do basically exactly the same thing there, but I'm showing you a different method to approach this. Any questions about any of this? Okay, I'll see you next week.